So the Poisson distribution can be approximated by a binomial distribution where the product of the parameters of the binomial distribution is equal to the parameter lambda of the Poisson distribution. What we are going to do is we are going to take the limit of n, take the limit of the PMF of the binomial distribution as n goes to infinity, and this product is kept constant, to obtain the PMF of the of the Poisson distribution. So here we have that. A Poisson lambda random variable is the limiting case of a binomial NP random variable as n goes to infinity. Obviously, when n goes to infinity, p goes to 0. Remember, p is the probability of having one event in a slot. When n goes to infinity, you have infinitesimally small slots, so the probability of an event in each one goes to 0. But the product, n times p, is constant at lambda. Okay, so the PMF of the Poisson distribution can be found by computing the limit as n goes to infinity with this constraint of the binomial distribution, and choose k times p to the power k, 1 minus p to the power n minus k. Okay, and k here can be any non-negative integer. Now, if you just expand this binomial term and choose k, that's n times n minus 1 times up to down to n minus k plus 1, and I have canceled out n minus k factorial in the numerator and in the denominator, and I have a k factorial from this n choose k term, and p to the power k is actually lambda to the power k divided by n to the power k, and I have 1 minus p to the power n minus k. So I write that as 1 minus p to power n times 1 minus p to power minus k. Now, I'm going to sorry. I'm going to arrange the terms a bit here. So I have lambda to the power k divided by k factorial, and I have this product here occurring here, and I have n to the power k here times 1 minus p to power minus k, and this one here, 1 minus p, I write as 1 minus lambda over n to the power n. Now here, observe, let me just erase these. Now observe each of these. Lambda to the power divided by k factorial. This term here is independent of n, so it will stay constant in the limit. Okay. The second term here, you see, the numerator is a polynomial in n with degree k, because I have k terms in the numerator all multiplied, and the leading coefficient is 1. The coefficient of n to the power k is 1. And in the denominator, I have n to the power k, another polynomial in n with degree k, and the leading coefficient is also 1. So the ratio of these two polynomials will be, when n goes to infinity, will converge to 1. So this thing at the limit will go to 1. Okay, and this one, 1 minus p to the power minus k. K is a constant integer. It's an integer, a finite number. But p, you see, as n goes to infinity, p goes to 0. Okay, so this term here, 1 minus p to the power minus k, whatever k is, at the limit will go to 1, because it will be, at the limit, this will be approaching 1, and that is to the power minus k. Whatever k is, it's an integer, but whatever its value, at the limit, this will be also 1. And finally, this term here, 1 minus lambda over n to the power n. Now, this is a bit tricky, because you see, lambda is constant, but n is going to infinity, so 1 minus lambda over n is going to 1. But the power is also going to infinity, so it's the indeterminate form of 1 to the power infinity, okay? But we know that, in general, for a real number a, 1 plus a divided by n to the power n as n goes to infinity is e to the power a. Okay, this is a well-known fact. You can find this from calculus books or online entries. It's not that difficult to show this, but of course I'm not going to spend any time on this. But this helps us to obtain the limit of this as e to the power minus lambda at the limit. So what we have here is this is 1, this is 1. I have lambda to the power k divided by k factorial multiplied by e to the power minus lambda. So this is the PMF of the Poisson distribution.